Hey everyone, I want to continue our discussion of dynamics and Newton's laws, and we're going to talk about Newton's second law. So Newton's first law, if you recall, was talking about why an object will end up moving using the concept of forces. So Newton's second law actually talks about exactly how it moves, and this actually leads us to our main equation for this unit. This is an equation that we're going to use all throughout this unit and in future units. So the way that the law is phrased is that it says that the relationship between the net force, the mass, and the acceleration is given by this equation, F net equals ma. This is a major equation, and like I said, it gets reused all the time. And this also allows us to relate the concepts that we're talking about in this unit of dynamics to what we've learned about in kinematics. For example, I can use this equation to figure out what my acceleration is, and then combine it with the kinematics equations from before to figure out things like your final velocity or the distance. So you might find that in some free response type questions where you'll have to use this equation first and then use the kinematics equation later on to find something else, or vice versa. Now, just to clarify, the net force, this is referring to the total force acting on the object. So we talked about how we can kind of look at the net force on an object, if you remember. We know how to find the net value of vectors. You know, you add vectors that go in the same direction, subtract vectors that go in opposite directions. So that's what's going to happen here. So we would add up all the forces that are acting vertically on the object, add up all the forces that are going horizontally on the object, and determine what the net effect force is. Just like how we found what the net displacement was, or the net velocity when we did the whole um, finding the resultant aspect. That's actually what net force is. It's the resultant force acting on an object. Now, one thing I do want to point out is it's very common that the net force is probably only going to be in one of the two dimensions. The reason I'm saying that is you wouldn't really expect the object to be experiencing a net force in both the vertical and horizontal direction. It's almost kind of like one or the other. All right, so like I said, this is just a really major equation. So it tells us how the force affects the acceleration on the object. Now, there is a slight aside that I need to talk about, and it's this concept about inertial and gravitational mass. Now, I really don't like this idea. I don't like talking about it because it's kind of pointless, as you'll see, but it's something that I have to do because the AP1 really does like to ask this question frequently, at least once every exam. It's a very easy question, though. I will point out that. So, what is inertial mass and gravitational mass? Well, inertial mass refers to the fact that if you use an equation like F net equals ma, where you apply a force to an object, you measure the acceleration, and then use this equation to find the mass, that mass is called inertial mass. That's basically it. So the inertial mass refers to the mass when you determined when you use this equation. Gravitational mass uses a slightly different equation, which is Fg equals mg. Now, you may notice this actually is pretty much this equation. It's got a force, a mass, and a form of acceleration. Force, mass, acceleration. This actually is a reworked version of this equation. That's how it's derived. If you recall, if you have an object in free fall, there's only one force acting on it, the force of gravity. So in this case, the net force would be the force of gravity. And we also know from the kinematics unit that when an object's in free fall, the acceleration is represented by the letter g for 9.8, or the acceleration of gravity. So for an object in free fall, we could say that Fg equals mg. So if we use this equation, and I want to actually go back, that doesn't mean that this equation only works for an object in free fall. This is just how it's derived. It's used all the time. So anytime you want to find the weight of an object, we talked about how the force of gravity is always present on every object. So this means this is going to be another main staple equation. Now, I want to going back to that. So this equation, if we use this equation to find the mass of the object by measuring the force of gravity or the weight of the object using the acceleration of gravity and then finding the mass, that mass is called the gravitational mass. So what's the difference? Nothing. The idea between the inertial mass and the gravitational mass is how you go about finding it. Inertial mass uses the concept of acceleration. Gravitational mass uses the concept of gravity. What I usually tell students is this, because the way the question is worded is they'll ask you what type of experiment will find the inertial mass, or what type of experiment would find the gravitational mass? And the rule of thumb is this: if the experiment would work in space, it's the inertial mass. If the experiment requires gravity, it requires you to be on Earth, then it's the gravitational mass. A perfect example is placing masses on a scale. So you might think that you're not using Fg equals mg when you place a mass on one scale and then try and put a mass on another, like using the triple beam. But that triple beam balance does not work in space because the whole point is that both sides are being pulled down by gravity. So in space, a triple beam balance no longer works. Therefore, that experiment putting things on scales would be a gravitational mass, not an inertial. That's basically it. Uh, when as we go through this unit and the other units, you'll see different types of experiments we can do and how we can kind of change that to find the different, well, how to find mass. And then you can kind of rank them and think, okay, would this work in space, or would this have to be done on a planet? All right. So here are some questions. So why don't you try using that equation on these two, and we'll work on this. All right. So here for question 7, they give us the net force. They give us an acceleration. So and they want to. Sorry, they give us a mass and acceleration, and they want the net force. So F net equals ma. Plug 123 in for the two numbers, and we get a net force of 2300 newtons. For number 8, they want the weight of a 100-kilogram object. So this is referring to Fg. So I'm going to use the equation Fg equals mg this time. I'm going to use the 100 kilograms and the 10 meters per second squared, since it's pretty much assumed to be on Earth. And we get that the weight is 1,000 newtons. Again, do not confuse weight and mass. All right, here's the next two. Work on these. All right. Question 9. The way we want to find the acceleration when we have this 5-kilogram object being lifted by a net force. So again, it's plug and chug. We plug the numbers into the equation. 100 equals 5a. Solve for a, and we get 20 meters per second squared. For number 10, they tell us two forces, and they want us to figure out, and they give us the mass, and they want us to find the net acceleration. So we're going to do the F net equals ma. This time, because I have the two forces, I have to subtract them. We have 50 to the right and 28 to the left. So they're going in opposite directions. 50 minus 28 gets me 22. So, set that equal, put that into the equation, set it equal to 20a, and we get that the acceleration is 1.1 meters per second squared. I didn't put a direction here, but it would be to the right, since that is the direction of the net force. The 50 newtons is larger than the 28. Therefore, the acceleration will always be also be in that same direction. All right, and this is the last question. All right, so here they want to know which one represents the force on the block by the table. This one can be actually done through process elimination. If you look through, choice 2 and 3 are measured in kilograms. Choice 4 is going down, and that's not how that works. Also, that's not an appropriate force, but we know that the normal force, the force exerted on the block by the table, would be going upwards. That's just a weird way of saying the normal force. So the answer is that. Uh, Here's the next question. We'll work on this, and we'll go over in a second. All right, so we have this, a man has a mass. They give us an acceleration of gravity on the moon, and they want to know what the mass on the moon is. This actually is the most common trick question that tends to get almost everyone every single time, because mass never changes. This is extremely important to remember. The mass is still 98 kilograms. It doesn't matter where you are in the universe, whether you're on Earth, on the moon, in the sun, or just in the vacuum of space. Your mass is always the same because your mass is the amount of matter you contain. Your weight is how that mass is affected by the effects of gravity. So your weight would be something like 98 times 1.62. I'm going to guess like about 160-ish. But your mass does not change. So this is something extremely important to keep in mind. And it's one of those very subtle things that they always throw in there to kind of trick people. So please, please, please don't fall for it. And I believe this is the last question. So work on this. We'll go over in a second. All right. So they give us this diagram, and they want to determine what the frictional force acting on the object is. So this is actually kind of the type of question that you would see. The other ones that we saw are kind of just foundational, trying to practice stuff. So how are we going to go about doing this? So we're trying to find this frictional force. We have no way of figuring this out. But the way that we want to go through this is we want to try and uh, get more pieces of information that we can. So I see acceleration here, and I see mass, and I see concept of forces. My mind immediately goes to F then equals ma. Let's find the net force. So in this unit, you should link acceleration to net force almost every single time. So anytime you see an acceleration, your mind should immediately jump to that first equation, F then equals ma. So we use that equation with the mass and the acceleration, and we get that the net force acting on the object is 40 newtons. So the net force is the sum of these two forces, or the resultant of those two forces. So these two forces will add up to 40. Now, it is important to keep in mind what direction the net force is, because because they're going in opposite directions, that means that one force is going to be 40 newtons larger than the other. However, which one's the larger one? Is it the frictional force that's larger, or is it the applied force that's larger? Because depending on the answer to that question, the frictional force value will be different. If frictional force is bigger, the answer would be 90, because 90 is 40 bigger than 50. If the applied force is bigger, then the frictional force is 10. So let's see. Well, the acceleration is going to the right, which means that the net force is also going to the right. So if the net force is to the right, that means this applied force has to be the bigger force. So this 50 is bigger than the frictional force. Now, to show this, you would write it like this: F net equals FAP minus F friction. Now, this actually can be found. The way I showed it just before, or the way I explained it, was kind of the conceptual idea. However, this would be a little bit more appropriate. So we know that the net force is going to be the sum of these two forces. And if you go by my designation of sign from before, that the direction of positive is the direction of acceleration. So this applied force is in the direction of acceleration, so it's positive. The frictional force is in the opposite direction of acceleration, so it's negative. So that's why we have F applied minus F of friction. So we plug in the the net force and the applied force, and we solve for friction, and we get the 10 newtons, like I said before. All right. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.